Here's a problem dealing with conservation of angular momentum. So, the basic idea with conservation of angular momentum is L1I plus L2I is equal to L1F plus L2F, right? Just like conservation of linear momentum. And we don't even have to divide it up into components because there's only forwards and backwards. Now, in this case, I'm going to write these out very carefully. Oh, darn it. Said I was going to be careful. Omega 2F, Omega 2F. Okay. Now, what I'm doing is I'm noting that I1I and I1F, I'm noting that the moment of inertia can change. Right? Because unlike with momentum problems, you got MV, and M doesn't change. Right? The M1, you don't have M1I and M1F because the mass isn't changing. But the moment of inertia depends on mass and position. And the position can change. So, let's take the merry-go-round as object number 1. Okay? So I1I is the moment of inertia for the merry-go-round. Now the merry-go-round has the moment of inertia of a cylinder. So that's 1/2 mr squared. And we are told that the merry-go-round has a mass of 250 and a radius of 1.7 meters. So that's 361.25. Now, during this problem, the moment of inertia of the merry-go-round itself doesn't change. The merry-go-round is not changing its radius, it's not changing its shape or anything like that. So I1F is also 361.25. Now let's consider the person. The moment of inertia for the person is orbiting around the center of the merry-go-round and has a moment of inertia of mr squared. I guess I'll put Ri here. So the person is initially on the rim of the merry-go-round, and the person has a mass of 95. So the rim of the merry-go-round, that's radius 1.7 squared, and so the person's initial angular momentum, or the initial moment of inertia, is 274.55. Alright? But then the person walks inward to a radius of 75 centimeters, so the final moment of inertia for the person is different. It's 95 times 0.75 squared, which is 53.44. Okay? Now let's look at the angular speeds. It says initially both are moving at an angular rate of 12 revolutions per minute. So the initial omega 1I, and omega 2I are both 12 revolutions per minute, which if we convert that, it's 1.26 radians per second. Alright? And what we're looking for is omega F. Now both of them move together, so that means I can simplify the equation, right? I can simplify both the first part and the second part. The first part of the equation I can write like this, and the second part of the equation, this is I1F plus I2F. Right? I can write both sides of the equation like that. Yeah, so I need to find omega F for part A. It says what's the new angular speed of the system, so let me plug in what I know. Right, now that we've been real systematic about it, this should be very easy. Let's see, 361.25 plus 53 omega F. Right, now it's real easy to solve for omega F. I get 801.1 is equal to 414.7 omega F, and omega F is 1.9 radians per second. So there's the new angular speed of the system right there. Alright, we're not done. It says if the person is the only force doing work, how much work does the person do when walking? Okay, so if it's asking for the work done by a force, right? So the work done by a force can be found with F delta S cosine theta, but we have no idea what the person's force is, nor do we have any idea what delta S is. I mean, yeah, she moves, 1.15 meters inward, but she's not moving in a straight line. She's curling around in some kind of spiral pattern. God knows what theta is, so forget that. Her force doesn't have any potential energy associated with it. So the way you got to do this, the way you got to find this work, is with, when you've got the works done by several different forces is equal to delta K, and if you know all the other works in the problem, you can solve for that unknown work. That's what we're going to have to do here. So let's consider the work-energy theorem here, the sum of the works done by all forces. Well, the sum of the works done by all the forces in this problem is just the work done by the person. Right? It says that the person is the only force doing work in the problem. That's equal to the change in kinetic energy. So if I can find the change in kinetic energy, then that's the work done by the person. So let's do that. The initial kinetic energy is, now since they're both moving together, we can just write it like this. 1/2 I1 plus I2 omega I squared, right? Remember that the kinetic energy is written as 1/2 mv squared plus 1/2 I omega squared, right? But we only need this part if it's translating, right? If the merry-go-round were, I don't know, rolling along the street or something, then yeah, we'd need that. This is the rotation. The merry-go-round is only rotating, so this is all we need. So if I use my values from above for I1I and I2I and omega 1I, I get 504.7. Oops, 504.7 joules. Now the final kinetic energy, 1/2 I1F plus I2F omega F squared. Again, plugging in my value for omega F here and my values for I1F and I2F, I get 748.5. Okay, and so the change in kinetic energy, the work done by the person, is equal to the change in kinetic energy, Kf minus Ki, and that's about 240 joules. So there's your answer.